Hi everyone, and welcome back to the channel. This is the second part of the chapter 12 lecture regarding oxidation and reduction. There are three different types of reductions depending on how molecular hydrogen is added to the chemical structure. The first one here is by using the simplest reducing agent, which is molecular hydrogen. Reductions using molecular hydrogen are carried out with a metal catalyst. So we need a metal catalyst in order to speed up this reduction reaction. The second type of reduction reaction is by adding 2 protons and 2 electrons to a substrate, because essentially a molecular hydrogen is equivalent to 2 protons plus 2 electrons. Alkali metals are a good source of electrons. Alkali metals such as lithium, sodium, and potassium. Liquid ammonia, on the other hand, is a good source of protons. And these type of reduction reactions are known as dissolving metal reductions. The third type of reduction is known as hydride reduction, and this is done by adding a hydride and a proton by using sodium borohydride, NaBH4, or lithium aluminum hydride, LiAlH4. Both of these reagents deliver hydride to a substrate, and a proton is added from water or alcohol. So shown here is the chemical structure of sodium borohydride, NaBH4, and on the right hand side we have the structure of lithium aluminum hydride. So you can see here that both of these reagents are salts or inorganic compounds. Metal hydride reagents are a good source of hydride because if you look over here, they contain polar metal to hydrogen bonds that place a partial negative charge on the hydrogen atom. And this metal atom here can either be boron or aluminum. The first type of reduction reaction that we're going to focus on is known as catalytic hydrogenation, which is the type of reduction reaction involving molecular hydrogen in the presence of a metal catalyst. So here we have an alkene reacting with molecular hydrogen in the presence of a metal catalyst, and this gets converted into an alkane. So we know that this is a reduction reaction because of the fact that there was an increase in the number of carbon to hydrogen bonds. And we can double check that. You can always look at these 2 carbon atoms shown here. Focus on these 2 carbon atoms shown here and count the number of carbon to hydrogen bonds. So you'll see that there's a net change of 2 new carbon to hydrogen bonds. So an alkene has been reduced into an alkane. So this is just a general reduction reaction involving molecular hydrogen in the presence of a metal catalyst where an alkene is reduced into an alkane. And the typical metal catalysts that are used in this type of reduction reactions are palladium, platinum, and nickel that are adsorbed onto an inert solid like charcoal. And charcoal is just made up of carbon atoms. One important thing to note when it comes to catalytic hydrogenation is that the 2 hydrogen atoms in molecular hydrogen get added in a syn fashion. So in the first example here, we have pentene undergoing catalytic hydrogenation involving molecular hydrogen in the presence of a metal catalyst, which is palladium, adsorbed on charcoal. So you can see that these 2 hydrogen atoms get added to the 2 carbon atoms that were originally involved in the pi bond in a syn fashion. So this syn addition becomes very important when it comes to stereochemistry. So here in the second example, we have dimethylcyclohexene undergoing catalytic hydrogenation. Again, the 2 hydrogen atoms get added to these 2 carbon atoms that were originally involved in the pi bond in a syn fashion. So you can see that these 2 hydrogen atoms are added on the same side. Here's practice problem number 2. What alkane is formed when each alkene is treated with molecular hydrogen in the presence of a palladium catalyst? So for the first one here, the first thing that I would do is to write down the actual chemical reaction equation as shown here. So we're reacting it with molecular hydrogen in the presence of a palladium adsorbed on charcoal. So for the product, which is going to be an alkane, is to actually draw the reaction again, or I'm sorry, the structure of the alkene, and you can see that this alkene has a hydrogen that's bonded to this carbon already. And so the first thing that I would do after drawing this is to add the two hydrogen atoms in the syn fashion. Okay, so at this point, it doesn't really matter whether it's going to be syn addition or not, but it's just a good practice to add these two hydrogen atoms in a syn fashion. So you can see that they're on the same side of the two carbon atoms. And then what I would do next is to remove this double bond, right? Because we're breaking this pi bond here. All right, so this is the product, the alkane that's formed when this alkene is undergoing catalytic hydrogenation. And we can clean up this chemical structure a little bit as shown here. So this is the final product. And for the second molecule here, we can do the same thing. We can draw the chemical reaction equation. So we have the alkene that's undergoing catalytic hydrogenation involving molecular hydrogen in the presence of a metal catalyst. And the next thing that I would do here is to redraw the molecule. And just this is to show you that there's a hydrogen again that's bonded to this carbon atom. And then we're going to add the two hydrogen atoms coming from the molecular hydrogen onto these two carbon atoms that were originally involved in the pi bond, as shown here. And then we're going to remove this double bond here because we're breaking the pi bond. Alright, and then we can just clean up this chemical structure as shown here. So this is the final product of this catalytic hydrogenation reaction. And for the third one here, again, here's the chemical reaction equation, and I'm going to redraw the molecule as shown here. Again, you can see that there is a hydrogen that's bonded to this carbon atom, and all we have to do is add the two hydrogen atoms coming from the molecular hydrogen onto these two carbon atoms involved in the double bond, as shown here. So I decided to put them in the back in a syn fashion, you can see here, and we're going to get rid of the pi bond, the double bond here. Alright, and we can clean this up a little bit, and this is the final product of this reaction. Here's practice problem number 3. Draw all alkenes that react with one equivalent of molecular hydrogen in the presence of a palladium catalyst to form each alkene. Consider constitutional isomers only. So this question is basically asking what kind of alkenes do we start out with in order to get these alkanes shown here as the products of hydrogenation reaction. So for the first alkane structure shown here, the first thing that I would do is to draw the structure of the alkane. And then we're going to work backwards and find out what kind of alkene we need to undergo reduction reaction via catalytic hydrogenation to get this alkane structure. And you already know that a catalytic hydrogenation reaction replaces a double bond with two hydrogen atoms. And so if we work backwards, right, we're going to react an alkene with molecular hydrogen in the presence of a metal catalyst to get this structure shown here. And so the easiest way to do this is to draw the alkane structure and then just start adding double bonds, right? So you can have this alkene shown here as one potential alkene isomer, constitutional isomer, that undergoes catalytic hydrogenation reaction and end up with this alkane right here. All right, so this is one potential answer to this question. Another one is when you have a double bond here instead, as shown here. So you can have a double bond here. So this alkene would also undergo catalytic hydrogenation reaction to get this product shown here. And finally, you can also have this alkene where the double bond is on the first carbon atom, the first two carbon atoms, as shown here. And for the second part here, we're going to do the same thing. We're going to draw the structure of the alkane, as shown here, and we're going to work backwards to figure out what kind of alkenes can undergo hydrogenation and end up with this alkane structure. So we're just going to be adding double bonds within the structure to form the alkene. But you have to be careful because we can't put a double bond anywhere around this carbon atom because this carbon atom is already tetrasubstituted. And so we can put a double bond here, and that would be one of the isomers. We can also put a double bond here between these two carbon atoms, and that's going to be another isomer. If you put a double bond here, that's also a possibility, but then it would be the same as the one that has a double bond on this side. So here's the first isomer where the double bond is up top. You can also put the double bond here at the bottom, but they would be the same identical molecule. The second potential alkene would have the double bond here between these two carbon atoms, or you can also have them between these two carbon atoms. It doesn't really matter because, again, those two are identical molecules. So these two alkenes are constitutional isomers that can undergo hydrogenation reaction and will form the same exact alkane, which is this product here. And finally, for the third part here, we're going to do the same thing. We're going to draw the structure of the product, which is the alkane here, and we're going to work backwards and figure out what kind of alkene structures are possible. So for the first one, we're just going to add a double bond here for the first two carbon atoms. And then a second possible constitutional isomer would have the double bond over here. And then we're just going to go around the structure. So we're going to have the double bond between these two carbon atoms. And then double bond between these two carbon atoms. And then finally, double bond between these two carbon atoms here. All right, so for the third example, we have a total of 5 alkene isomers, constitutional isomers, that can potentially undergo catalytic hydrogenation reaction and end up with this cycloalkane here.